Section 17.4, Series Solutions. Sometimes differential equations have solutions that cannot be written in terms of elementary functions, but we can still solve those differential equations if we assume that the differential equation has a solution that can be written in the form of a power series. So we do that, we solve for the coefficients of the power series, similar to the way that we solved using the method of undetermined coefficients for non-homogeneous linear equations. And then we can, check later to make sure it's a solution to the differential equation that we started with. For our first example, how about we try to solve a differential equation that doesn't really need a power series solution. Notice this is a simple homogeneous linear equation that we could already solve pretty easily, but we'll use power series just to demonstrate the method because it'll be easier to use power series for an easier problem, and then we can do it later for a problem that really requires it a little bit more. So for this problem, it's a little bit overkill, but that's okay. So we'll set our solution y equal to a power series, so it'll have some first constant c0 and then some constant c1 times x plus another constant c2 times x squared plus c3 times x cubed, and so on. And we can write that using sigma notation as the series from n equals 0 to infinity of Cn x to the n. And then in order to figure out what all these coefficients are, how about we take the derivative? So remember, we differentiate power series term by term, so c0 disappears because it's a constant. We'll get c1 plus 2 times c2x using the power rule, plus 3 times c3 times x squared, and so on. So that just becomes the sum from n equals 1 to infinity of n times cn times x to the n minus 1 now. Let's also take our second derivative because in our differential equation we have the second derivative. So we'll get 2 times c2 plus 2 times 3 times c3 times x, and so on. So writing that as a series, that's the sum from n equals 2 to infinity of n times n minus 1 times cn times x to the n minus 2. Now notice we're going to want to plug these both back into our differential equation, and this series for y starts at 0, but this series for y double prime starts at 2. So how about we make a substitution? We'll replace n with n plus 2, and that way we can start at 0. So substituting in n plus 2 for n, our limit changes from n equals 2 to n equals 0. N gets replaced with n plus 2, n minus 1 gets replaced with n plus 1, and then cn becomes cn plus 2, and x to the n minus 2 becomes x to the n. So now what we can do is plug this equation this expression for y and this expression for y double prime into our differential equation. So we get the sum from n equals 0 to infinity of n plus 2 times n plus 1 times cn plus 2 x to the n plus the sum from n equals 0 to infinity of cn x to the n equals 0. So what we can do is combine our sums because they both have the same summation. So what we'll get is the sum from n equals 0 to infinity of n plus 2 times n plus 1 times cn plus 2, and we can factor out there's an x to the n in both. So plus cn times x to the n. That must be 0. Well, notice on the right side, there are no x to the n's. There are 0 x to the n's. So that means that this coefficient must be 0. So we have n plus 2 times n plus 1 times cn plus 2 plus cn equals 0. And we can solve for cn plus 2 in terms of cn. So we can get cn plus 2 equal to minus cn over n plus 1 times n plus 2, where n goes from 0, 1, 2, 3, and so on. So this is called a recursion relation. What we can do is we can put in values of n so that we can get all of the coefficients cn in terms of just 2 of them. We can do it all in terms of the first 2, because notice we have cn plus 2 defined by cn, so everything's already written in terms of 2 of the coefficients. So what we'll do is we'll figure out what all of the other ones are using just c0 and c1. So to do that, we'll start with n equals 0. We'll plug that in, and we'll see that that gives us c2 equal to negative c0 over 1 times 2. If we plug in n equals 1, then we get c3 equal to negative c1 over 2 times 3. If we plug in n equals 2, then we'll get c4 equal to negative c2 over 3 times 4. But remember, like I said, we want to try to make all of these in terms of c0 and c1. So what we'll do is we'll replace c2, because we solved for c2 in terms of c0. So c2 is negative c0 over 1 times 2, so the negative cancels, and we just get c0 over 1 times 2 times 3 times 4. So that's just c0 over 4 factorial. Let's try n equals 3 now. We'll do n equals 3. We'll see that that tells us that c5 is equal to negative c3 over 4 times 5. So that's, we replace c3 with negative c1 over 2 times 3. So that's just c1 over 2 times 3 times 4 times 5. Negative cancels. We'll end up with c1 over 5 factorial. So let's do a couple more. We could do n equals 4 and see that that gives us c6 equal to negative c4 over 5 times 6. So that's negative c0 over 4 factorial times 5 times 6, which is negative c0 over 6 factorial. And if we just plug in n equals 5, we can see that c7 is equal to negative c5 over 6 times 7, so that's negative c1 over 5 factorial times 6 times 7, which is negative c1 over 7 factorial. So it looks like we've identified a pattern. It seems like if we look at the even coefficients, or the even term coefficients, separate from the odd ones, it looks like they alternate. They go from negative to negative, back to positive, we can assume. And it looks like they all have a factorial on the bottom that's even. So just, we could write that as 2n factorial. Similarly, if we look at the odd numbered coefficients, they also alternate. We have negative, positive, negative, and their denominator is just an odd factorial. So how about we write that? We could say that C2n for the even coefficients is alternating, so negative 1 to the n, and it's C0 on top, and 2n factorial on the bottom, because it was c0 in every single one of those. But for the odd coefficients, we have c2n plus 1, and that'll be alternating also, and then there's c1 on top, and 2n plus 1 factorial on the bottom, and odd factorial. So that means that we could write our solution y equals c0 plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth plus c5x to the fifth, etc., as c0 times 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on, with a general term of negative 1 to the n, x to the 2n over 2n factorial, and so on. And that's just our even coefficients, so we also need our odd ones, so we'll add c1 times x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on until we get to an arbitrary term of x to the 2n plus 1 over 2n plus 1 factorial, and then we keep going. So notice though that this thing could be written using sigma notation, as could this, so we could rewrite our y as c0 times the sum from n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial plus c1 times the sum from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And this is actually kind of cool because notice this is just the Maclaurin series for cosine times c0. This is just the Maclaurin series for sine times c1. So what we could do is we could write our solution y of x equal to c0 cosine x plus c1 sine x, even though we usually can't do this because usually our series that we get in our answers will not be representative of some elementary functions that we know of. But in this case, remember this was the same example that we did in section 17.1. It was the sixth example we did with the initial value problem. And remember that the equation that we had was y double prime plus y equals 0. So the auxiliary equation is r squared plus 1 equals 0. So our roots were plus or minus I, and thus our solution matches with the solution that we got. Y of x equals c0 cosine x plus c1 sine x. Let's do an example where our solution will not be in terms of elementary functions. So first we'll write our solution, y equals the sum from n equals 0 to infinity of cn x to the n, our power series. We're assuming that this thing has this as a solution, and then we'll see what we get, assuming that it does. So we'll take the derivative, and we'll get that that's the same as before, n equals 1 to infinity n times cn x to the n minus 1, and y double prime, as before, is the sum from n equals 2 to infinity of n times n minus 1 times cn x to the n minus 2, and as before, we'll make our change of variable to start at 0. We'll just replace n with n plus 2, and we get n plus 2 times n plus 1 times Cn plus 2x to the n. And now we'll replace everything in our differential equation. So we'll replace y double prime with the sum from n equals 0 to infinity of n plus 2 times n plus 1 times Cn plus 2x to the n minus 2x times y prime, so that's 2x times the sum from n equals 1 to infinity of n Cn x to the n minus 1 plus y, which is just the sum from n equals 0 to infinity of Cn x to the n. And all that's supposed to equal 0. So we can simplify this a little bit and throw in the x and throw in the 2. So let's do that. We'll rewrite the sum from n equals 0 to infinity of n plus 2, n plus 1, Cn plus 2 x to the n, and then we'll write the next term as the sum from n equals 1 to infinity, next bunch of terms, to n Cn x to the n. We just increase this by 1 by throwing in the extra x. And then this is the sum from n equals 0 to infinity of Cn x to the n. Notice we do not have to rewrite this starting at 0 because it already is the same thing. If you start at 0, then you're plugging in 0, right? So just plugging 0 for n. Notice this entire thing would be 0. Adding 0 to this is the same as just having this start at 1. So you could start at 0 and it makes no difference. So that means that we can just imagine that this thing is starting at 0 instead of 1, doesn't really matter. And that means that we can combine all of our series in order to get the sum of n plus 2 times n plus 1 times Cn plus 2 minus 2n minus 1 times Cn, and we'll factor out the x to the n. So this should be 0. As before, because we have no x to the n's on the right side, that means that the coefficient is 0. So that means that we have n plus 2 times n plus 1 times Cn plus 2 minus 2n minus 1 times Cn equal to 0. So this means that we get, solving for Cn plus 2, we have Cn plus 2 equal to 2n minus 1 over n plus 1 times n plus 2 times Cn, where n goes from 0 to 1, 2, 3, etc. Okay, so let's plug in a whole bunch of values for n so we can identify the pattern of the coefficients and express everything in terms of C0 and C1. So we'll start with n equal to 0, and then that'll give us C2 equals negative 1 over 1 times 2 times C0. N equals 1 gives us C3 equal to 1 times 2 times 3 times C1. N equals 2 implies that C4 is equal to 3 over 3 times 4 times C2. And we solve for C2, so we'll plug that in for C2 and replace it. And we get negative 3 over 1 times 2 times 3 times 4 times C0, which is negative 3 over 4 factorial times C0. Then we'll look at n equals 3, where we get C5 equal to 5 over 4 times 5 times C3. So that's 1 times 5 over 2 times 3 times 4 times 5 times C1, which is 1 times 5 over 5 factorial times C1. Then n equals 4, gives us C6 equal to 7 over 5 times 6 times C4, replace C4, and then we get negative 3 times 7 over 4 factorial times 5 times 6 times C0, which is negative 3 times 7 over 6 factorial times C0. Let's do a couple more. For n equals 5, we get C7 equal to 9 over 6 times 7 times C5. We replace that, we get 1 times 5 times 9 over 5 factorial times 6 times 7 times C1, which is 1 times 5 times 9 over 7 factorial times C1. Let's do a couple more just so we can be sure of our pattern. So for n equals 6, we have C8 equal to 11 over 7 times 8 times C6, which is negative 3 times 7 times 11 over 8 factorial times C0. Then n equals 7 gives us C9 equal to 13 over 8 times 9 times C7, which is 1 times 5 times 9 times 13 over 9 factorial times C1. So notice we had to do a few more because the pattern is not as obvious as it was last time, but now it becomes a little bit more clear. It looks like when we have odd numbers, we just keep multiplying numbers that are 4 apart. So we go 1, 5, 9, we would expect the next one to be 13, and then 17, etc. Whereas if we're even, we go to 3, 7, 11, etc. See how it holds even if you go back. Also notice that the even terms do not alternate, they're all negative. But the odd terms don't alternate either. Those are also all positive in this case. So that means that we could write our even terms C2n equal to negative 3 times 7 times 11, etc., with a general term of 4n minus 5. And we'll put that over even factorial 2n factorial times C0. And then our odd term coefficients are 1 times 5 times 9, and so on, with a general term of 4 minus 3. And that's over 2n plus 1 factorial times C1. So this means that we can write our solution, which was y equals C0 plus C1x plus C2x squared plus C3x cubed plus C4x the fourth, and so on, as C0 times 1 minus 1 over 2 factorial times x squared minus 3 over 4 factorial times x to the fourth minus 3 times 7 over 6 factorial x to the sixth minus 3 times 7 times 11 over 8 factorial x to the eighth minus so on, plus, so that was our even coefficients, plus our odd ones, which give x plus 1 over 3 factorial x cubed plus 1 times 5 over 5 factorial x to the fifth plus 1 times 5 times 9 over 7 factorial x to the 7th, and 1 times 5 times 9 times 13 over over 9 factorial x to the 9th, and so on. And if we're feeling very adventurous, we can write this using sigma notation as 1 minus 1 over 2 factorial x squared minus the sum from n equals 2 to infinity of 3 times 7 and so on times 4n minus 5 over 2n factorial x to the 2n plus c1 times x plus the sum from n equals 1 to infinity of 1 times 5 times 9 and so on till 4n minus 3 over 2n plus 1 factorial x to the 2n plus 1. And notice that we do not have elementary functions in this case, but it's still a perfectly valid solution. You could take this and plug it in to our differential equation, take the derivative, etc., and see that it actually is a solution that satisfies it. We could check it. We won't because it seems like a lot of work, but what we could do is imagine that we had an initial value problem. So let's say we still had y double prime minus 2x y prime, and I missed my x, to xy prime plus y equals 0, and we had the initial value y of 0 equals 0 and y prime of 0, let's say it was equal to 1. In that case, notice plugging in 0 for y kills off all of these guys. They all become 0. So we're just left with c0 times 1. So that means that c0 is equal to y of 0, which is 0, and c1 is similar. You could just take the derivative. You see that c1 times 1 is going to be the only thing that doesn't kill off when you plug in x equals 0. So that'll be y prime of 0, which is 1. So that simplifies things a lot, because if c0 is 0, this entire thing disappears. So all we have left is this thing times 1. So that means the solution to the initial value problem would just be y of x equals x plus the sum from n equals 1 to infinity of 1 times 5 times 9 times etc. till we get to 4n minus 3 over 2n plus 1 factorial x to the 2n plus 1, because only the odd coefficients remain. And this wasn't really part of our problem, but it's interesting to consider how simpler we get solutions, provided that we have some initial conditions.